In this lecture, we give a brief introduction to the sheaf cohomology. Here is the main motivation. For a short exact sequence 0 to f1 to f2 to f3 to 0, it's of sheaves on a scheme. Taking global section is only left exact, which means that it gives an exact sequence of group. However, the last map in general is not surjective. A counterexample can be seen as follows. Consider the double skyscraper sequence. Here, H is evaluation at point PQ, where PQ are 2 points in the projective line. This is an exact sequence, but H is not surjective on global sections as OXX. The global section is isomorphic to the field K. It only contains constant function. Hence, the pre-sheaf image H. Its global section is K. It contains constant function on the set PQ. However, on the right, Kp direct sum Kq x is K squared. Therefore, H is not surjective on sections, but H is surjective since sheafification will make this condition local, and image H as sheaf will isomorphic to Kp direct sum Kq. Cohomology will give a natural way to extend the sequence to the right. So there will be a long exact sequence like this. Quite often, there are explicit ways to compute this group. In fact, they turn out to be zero in many cases, so that this is a priori infinitely long exact sequence will usually break up into small and easily trackable pieces. The cohomology of sheaves can be defined for any sheaf of abelian group to a topological space, but in order to avoid technicalities, we restrict to the case of quasi-coherent sheaves on varieties in our notes. In case of the affine variety, which means that X equals spectrum of R, and we have an exact sequence of quasi-coherent sheaves with Fi equals Mi tilde for R modules Mi. This means that the corresponding sequence 0 to M1 to M2 to M3 to 0 is exact. This is just the sequence of global sections. Hence, the problem of the sequence of global sections not being exact goes away in the affine case. It just arises from gluing of affine patches. Consequently, we construct the cohomology of sheaves by studying the gluing behavior. So let's give the definition of check cohomology. Let F be a sheaf on variety X. We fix a fine open cover U1, U2, UR of X. Then we first define the K-vector space CPF like this. An element phi in CPF is just a collection of sections. It's a collection of sections phi I0 to IP for all intersections of P plus 1 sets taken from the children of fine open cover. Next, we define the boundary map D. dP is from CPF to CP plus 1F, and it sends phi to dP phi. And the dP phi has values at I0, IP plus 1 is this. Then we define the P cohomology of F. It's the kernel of dP quotient the image of dP minus 1. Its dimension as K-vector space is denoted by HP. So little h P is the dimension as K-vector space of the cohomology. As we have constructed, we had to pick an open affine open cover of variety X in order to define the cohomology of a sheaf on X. It is the crucial and non-trivial fact that up to isomorphism, the cohomology does not depend on this choice. In fact, there are other approaches to cohomology, for example, the derived functor approach, which never use affine open covers and therefore do not have this problem, but that, on the other hand, are essentially useless for actual computations. We will therefore continue to use our construction above, assume the independence of the chosen affine cover for granted. We will start with a few simple cases in which the cohomology of sheaves can be obtained immediately from the definition. So, let F be a sheaf on variety X. Then we have the following four properties. The first one says H0 is the global section. In fact, by definition, H0XF is the kernel of D0. And an element in C0F is given by phi I, which is section on UI, and the D0 of phi is like this. And by writing it equals 0 implies that phi I comes from a global section of F. So we have H0 XF isomorphic to Fx. And B says that if X are fine, then HPXF is 0. In fact, we have CPF is 0 by picking the affine open cover consists of the single set X. And to prove C, we use Kuhl's principal ideal theorem. Kuhl's principal ideal theorem tells that every irreducible component of Vf has dimension 1 in X. Then we can recursively pick non-constant homogeneous polynomials f0, fn, such that the dimension of X intersect with B f0 fi is less than n minus I for I equals 0, 1 to n, which means that X intersect with V f0 fn is empty set. So X is covered by the n plus 1 open components of V fi. So if this X, and we have that X is covered by the n plus 1 open complements of Vfi. So it's df1, df2, df3. But the open subsets are affine, so we can choose them as the affine open cover for the construction of cohomology. As this cover has n plus 1 subsets, we then have Cp is equals 0. Then our cohomology is 0 for p greater than n. And to prove D, we choose U1, UR be a fine open cover of Y. Then X intercept with U1, X intercept with UR is a fine open cover of X. Next, we show the most important tool for computing cohomology, which is the non-exact cohomology sequence arising from a short exact sequence of sheaves, which is the following proposition. Let 0 to f1 to f2 to f3 to 0 be exact sequence of sheaves on variety X. Then there is a non-exact sequence of vector space as follows. The main idea of the proof is to consider the following commutative diagram of linear map. The horizontal map are induced by morphisms of sheaves. And then we use the snake lemma. And we omit all the details. The most important example of sheaves are clearly the twisting sheaves on projective spaces. So let us explicitly compute their cohomology now. Let HP, Pn, or Pnd depends on 3 parameters. And we take a notational trick to simplify the computation. we will determine the cohomology of the quasi-coherent sheaf F be the direct sum of D in Z O P N D on Pn. The sections in F are of the form G divide F, where Fg is in K x0, xn, and F is homogeneous. And we can recover HP, Pn, OPND by taking the degraded parts of F. And we have the following property of cohomology of sheaves on Pn. In particular, this means that H0 Pn OPND, which is degraded piece of H0, is N plus D N and Hn Pn O Pnd equals minus D minus 1 N for D less than and HP Pn O Pn D equals 0 for other P and D. Here is the proof of the third property. For A, it follows immediately by the fact that H0 is just the space of global section. And for B, we compute directly by definition. We use the open cover by affine spaces UI. And then we have f of UI0 intersect UIP equals K x0 xn with localized as x0 xip. It is the vector space with bases the monomials x0 x xn kn, where ki0 kip is in Z, and all other exponents are non-negative. Relevant vector spaces for computation of Hn are CNF is a direct sum of K x0 xn localized at this, and Cn plus 1f is K x0 xn localized as this, and Cn plus 2f is 0. The cohomology is this. And it is the span of x0, k0, xn, kn with ki integer quotient by span x0, k0, xn, k0, and with 1 ki. and this quotient is this. And the last proposition says that HP is 0 for P not equal to 0 or n. We prove by induction on n. There's nothing to show when n equals 1 since HP is 0 for P not equal to 0 or 1. For n greater than 1, we consider the exact ideal sequence for inclusion of I. Then we have an exact sequence of quasi-coherent sheaves on Pn. Since OPND is locally free, thus taking tensor product with it keeps the sequence exact. Recall F is denoted by this. So after tensor with this, the previous exact sequence becomes and we know the fact that HP y s star f equals HP x f. Then we let x be p n minus 1, y be p n, and we have HP Pn s star f equals HP Pn minus 1f. And from this exact sequence, we have the non-exact sequence. And for p greater than 1 and less than n minus 1, we have so multiplication with x0 is an isomorphism from HP Pnf to HP Pnf. When p equals 0, it's less obvious, but one can deduce from this exact sequence that when p equals 0, multiply x0 is an isomorphism. When p is greater than 1, this is obvious. So the localization of HP x0 is HP Pn f is isomorphic to HP of U0, and it is 0. So for any phi in HP Pnf, x0 k phi equals 0, then phi is 0. and this implies that now we apply the theory of cohomology of sheaves to the classification of varieties. The idea is to consider dimensions of cohomology spaces for canonically defined sheaves. For example, structure sheaf or cotangent sheaf. To simplify computations, it is useful to consider linear combinations of them instead. From the non-exact sequence 0, H0, X. If all these elements are finite dimensional space, then we have the relationship of its dimensions, little h, x1 minus x2 plus, and this is 0. Then we can define the Euler characteristic of sheaf on X to be this, the alternating sum of little h. For example, we can calculate Euler characteristic of twisting sheaves on hyperspaces. Let X be hypersurface of degree D in Pn. And let E be any integer. Then we calculate this. Firstly, we know the Euler characteristic of Pn d is n plus dn. This follows directly from the fact that we have known all HP, Pn, O, Pn, d. And then we consider the exact ideal sequence induced by the inclusion map. This sequence remains exact with taking tensor product with this. So, but let's see this after tensor, it becomes this. And the isomorphism here follows by the fact that if we know an inclusion, then we have and we take F to be OX and G to be OPNE. Then after tensor with this, the exact sequence becomes the following. So what we want is the Euler characteristic of OXE. This is And then this equality follows the fact that the inclusion I to Pn and this equality follows by the additive of exact sequence of all the characteristics. Then finally, we have the remark that Hilbert polynomial can be defined in a cohomology way if F is a coherent sheaf over a projective scheme. Then we can define the Hilbert polynomial of F be P F n. And this function is indeed a polynomial. For large n, it agrees with the dimension of H0 x f n. And this equality follows by Serre's vanishing theorem.